Probability of compound events. When the outcome of one event does not affect the outcome of a second event, the two events are independent events. When the outcome of one event does affect the outcome of a second event, the two events are dependent events. When two events cannot happen at the same time, they are mutually exclusive. For example, being a girl versus being a boy. If A and B are not mutually exclusive, we use the following. The probability of A or B is equal to the probability of A plus the probability of B minus the overlap minus the probability of A and B. So recap for finding probability. To find the probability of two independent events both occurring, you multiply the probability of the first event by the probability of the second event. So if they don't affect each other, you can just multiply their separate probabilities. To find the probability of two dependent events both occurring, you multiply the probability of A and the probability of B after A occurs. So if we're talking about something like pulling a card out of the deck, you'd find the probability of pulling the first card, and then you'd multiply that by the probability that the second card is whatever you want, given that the first one was already chosen. So we would reduce the total number of cards. To find the probability of one or the other of two mutually exclusive events, you're going to add the probability of the first event to the probability of the second event. So keep in mind the keywords and things to look for. Typically, or you're going to be adding. Typically for and, you'll be multiplying. And then we just have to think about whether the two events affect one another and whether there's any overlap we have to consider. First example says, as part of a board game, you need to spin the spinner at right, which is divided into equal parts. Find the probability that you get 25 on your first spin and a 50 on your second spin. Well, first thing we have to do is think about whether these are independent or dependent events. Well, each time you spin the spinner is completely separate. One spin doesn't affect the next spin. So these are independent, so I'm just going to multiply their separate probabilities. So the probability of getting a 25, there's two regions labeled 25 of the total 1, 2, 3, 4, 5, 6, 7, 8 regions. And then the probability of spinning a 50 on the next one is 1 out of 8. So the probability of a 25 the first time and a 50 the second time is 2 out of 64, or 1 out of 32. Number 2. A bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and then randomly choose another grape. Find the probability that both events A and B will occur. So event A is that we choose green as our first grape. Event B is we choose green as our second grape as well. So the probability of choosing green and another green, well, there's 36 green grapes out of a total of 50 grapes, and I got that by doing 36 plus 14. So that's the probability that I choose a green grape the first time. The second time I'd be down to 35 green grapes out of a total of 49 grapes altogether. So to make this multiplying easier, I'm going to cross-reduce and make this 7 and this 10. They're both divisible by 5, so I'm going to reduce by 5, but then 7 over 49 reduces. And so I'm going to get 36 over 70, which I can reduce even further by 2 and get 18/35. You don't have to do the reducing, but I do recommend you find the simplified answer, especially in this case where it would have been so large originally. Example 3. A card is randomly selected from a standard deck. What is the probability that the card is a heart or a face card? Well, the probability of choosing a heart. Heart is one of the 4 suits of the deck, so it's a fourth of the deck, so that's 13 out of 52. Plus the probability of a face card. Well, face cards are Jack, Queen, King. And there's 4 suits, so there's 12 face cards out of 52. But we have to subtract out the overlap because there are 3 face cards that are hearts. The Jack of Hearts, the Queen of Hearts, and the King of Hearts. So we'd have 22 out of 52. Or if you choose to reduce, 11 out of 26. In a survey of 200 pet owners, 103 owned dogs, 88 owned cats, 25 owned birds, and 18 owned reptiles. No one owned both a cat and a bird. We can probably think about why. What is the probability that they owned a cat or a bird? So the probability of cat or bird. Well, 88 owned cats, so 88 out of the 200, plus 25 out of the 200. And since they told us they're mutually exclusive, none of them, no one had both the cat and the bird. We don't have to subtract out any overlap. We just go ahead and add. So we'll get 113 over 200. Of the response, 52 owned both a cat and a dog. So what's the probability of owning a cat or a dog? Well, again, the probability of a cat was 88 out of 200. The probability of a dog is 103 out of 200. And we have to subtract out the overlap because now we know there are 52 that did both. So we don't want to double count them. So we're going to have 88 over 200 plus 51 over 200. So we'll get 139 out of 200. Of the respondents, 119 owned a dog or a reptile. So what is the probability that they owned a dog and a reptile? Well, normally we would do the probability of a dog plus the probability of a reptile minus the probability of dog and reptile. In order to get the probability of a dog or a reptile. But now I'm going to subtract this to the other side. And then add this to the other side. So that my formula is now solved for the probability of a dog and reptile. And I can see that's going to equal the probability of the dog plus the probability of the reptile minus the probability of dog or reptile. So the probability of a dog is 103 out of 200. Probability of a reptile is 18 out of 200. And we're going to subtract away from that the probability of one or the other, which is 119 out of 200. And so we'll have 4 out of 200. I'm sorry, 104 out of 200. Probability of the complement of an event. So sometimes it's easier to find the probability that something's not going to happen than the probability that it is. And that's what we're talking about here. So if you are given the probability of an event, and we're going to refer to it as capital A, the probability of its complement so its opposite, which we show as A bar, can be found by subtracting the given probability from 1. And that's because all probabilities are totaled out of 1, and if they're completely mutually exclusive, you're either this or you're that, then the difference between 1 and the probability of the other event occurring would leave you with the probability of your event occurring. If the probability that a flight will be delayed is 0.21, then the probability it will not be delayed must be, we do 1 minus 21, 0.21, and we get 0.79. So the probability that it will not be delayed is approximately 79%. When two six-sided dice are tossed, there are 36 possible outcomes. Find the probability that the sum is not 8. So first thing we're going to do is create a little cheat chart. So we're going to find the sum of two dice. So we've got one set of dice down the left-hand side, the other across the top. So if they each would spin a 1, we'd have a sum of 2. 1 plus 2 would give us 3, 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6, 1 plus 6 is 7. And then you just keep going like that. Okay, so there are all the possibilities for the sum of two dice, and they wanted the probability that the sum is not 8. Well, the probability that it is 8, 1, 2, 3, 4, 5 different ways it can happen out of the total 36 different ways. So the probability that it's not an 8 equals 1 minus 5 out of 36. So you'll get 31/36. Last part of the example here, the sum is greater than or equal to 4. Well, that's going to equal 1 minus the probability that it equals a 4. And the probability that it equals 4, 1, 2, 3. There's only 3 ways it can happen out of 36. So you get 33/36. Or if you'd like to reduce, divide by the 3 and you'll get 11/12. So with compound events, you've got to think about whether one event occurs and then it affects the other event, or if they're mutually exclusive. Solving for or and in our formula is pretty much the same. So good luck going through and finding out your compound probabilities.